Forced induction is the process of delivering compressed air to the intake of an internal combustion engine. A forced induction engine uses a gas compressor to increase the pressure, temperature and density of the air. An engine without forced induction is considered a naturally aspirated engine. Introduction. Forced induction is used in the automotive and aviation industry to increase engine power and efficiency. A forced induction engine is essentially two compressors in series. The compression stroke of the engine is the main compression that every engine has. An additional compressor feeding into the intake of the engine causes forced induction of air. A compressor feeding pressure into another greatly increases the total compression ratio of the entire system. This intake pressure is called boost. This particularly helps aviation engines, as they need to operate at higher altitudes with lower air densities. Higher compression engines have the benefit of maximizing the amount of useful energy evolved per unit of fuel. Therefore, the thermal efficiency of the engine is increased in accordance with the vapor power cycle analysis of the second law of thermodynamics. The reason all engines are not higher compression is because for any given octane, the fuel will prematurely detonate with a higher than normal compression ratio. This is called preignition, detonation or knock and can cause severe engine damage. High compression on a naturally aspirated engine can reach the detonation threshold fairly easily. However, a forced induction engine can have a higher total compression without detonation because the air charge can be cooled after the first stage of compression, using an intercooler. One of the primary concerns in internal combustion emissions is a factor called the NOx fraction, or the amount of nitrogen, oxygen compounds the engine produces. This level is government-regulated for emissions as commonly seen at inspection stations. High compression causes high combustion temperatures. High combustion temperatures lead to higher NOx emissions, thus forced induction can give higher NOx fractions. Types of compressors. Two commonly used forced induction compressors are turbochargers and superchargers. A turbocharger is a centripetal compressor driven by the flow of exhaust gases. Superchargers use various different types of compressors but are all powered directly by the rotation of the engine, usually through a belt drive. The compressor can be centrifugal or a Roots type for positive displacement compression. An example of an internal compressor is a screw-type supercharger or a piston compressor. Turbochargers. A turbocharger relies on the volume and velocity of exhaust gases to spin spool the turbine wheel, which is connected to the compressor wheel via a common shaft. The boost pressure made can be regulated by a system of release valves and electronic controllers. The chief benefit of a turbocharger is that it consumes less power from the engine than a supercharger. The main drawback is that engine response suffers greatly because it takes time for the turbocharger to come up to speed, spool up. This delay in power delivery is referred to as turbo lag. Any given turbo design is inherently one of compromise. A smaller turbo will spool quickly and deliver full boost pressure at low engine speeds, but boost pressure will suffer at high engine RPM. A larger turbo, on the other hand, will provide improved high rev performance at the expense of low end response. Other common design issues include limited turbine lifespan, due to the high exhaust temperatures it must withstand, and the restrictive effect the turbine has upon exhaust flow. Superchargers. Superchargers have almost no lag time to build pressure because the compressor is always spinning proportionally to the engine speed. They are not as common as turbochargers because they use the torque produced from the engine to operate. This results in some loss in power and efficiency. A Roots-type supercharger uses paddles on two rotating drums to push air into the intake. Because it is a positive displacement device, this compressor has the advantage of producing the same pressure ratio at any engine speed. A screw-type supercharger is also a positive displacement device, like a Roots-type supercharger. Screw-type superchargers are more complex to manufacture than Roots-type superchargers, but are more efficient to operate, producing cooler air output. A centrifugal-type supercharger is not a positive displacement device and will usually have better thermal efficiency than a Roots-type supercharger. Centrifugal superchargers are also more compact and easier to use with an intercooler. Intercooling. An unavoidable side effect of forced induction is that compressing air raises its temperature. As a result, the charge density is reduced and the cylinders receive less air than the system's boost pressure prescribes. The risk of detonation, or knock, greatly increases. These drawbacks are countered by charge air cooling, which passes the air leaving the turbocharger or supercharger through a heat exchanger typically called an intercooler. This is done by cooling the charge air with an ambient flow of either air-air intercooler or liquid-to-air intercooler. The charge air density is increased and the temperature is reduced. In this way, an intercooler can greatly increase the ability to run higher absolute compression ratios and take full advantage of using compressors in series. The only drawbacks of intercooling are the intercooler's size, typically close to the size of a radiator, and the associated plumbing and piping. Topic: Water injection. Water injection is another effective means of cooling the charge air to prevent detonation. Methanol is mixed with the water to prevent freezing and to act as a slower-burning fuel. Water injection, unlike nitrous oxide or forced induction, doesn't add much power to the engine by itself, but allows more power to be safely added. It works by being sprayed into the compressed air charge. The water absorbs heat as it evaporates to cool the charge and lower combustion temperatures. The alcohol is also a fuel in the charge which burns slower and cooler than gasoline. Due to the lower intake temperatures and denser air charge, more boost pressure and timing advance can be safely added without using higher octane fuel. It is most often used in racing applications, however it was also shown to be practical for extended use. Diesel engines. Four-stroke. Diesel engines do not have pre-ignition problems because fuel is injected at the end of the compression stroke, therefore higher compression is used. Most modern diesel engines use a turbocharger. This is because the exhaust from a diesel is exceptionally strong, making it excellent for powering a turbo. The range of engine speed is narrower, allowing for a single turbo to fully power the entire engine range. Turbochargers can also achieve higher boost pressure than superchargers, which is necessary for most diesels. Two-stroke. Diesel two-strokes work in a different way to petrol ones and must have some form of forced induction, generally a supercharger, to work at all. Design considerations. The design of gasoline engines and the compression ratio impact the maximum possible boost. To obtain more power from higher boost levels and maintain reliability, many engine components have to be replaced or upgraded from that of naturally aspirated powertrains. Design considerations include the fuel pump, fuel injectors, pistons, connecting rods, crankshafts, valves, head gasket, and head bolts. The maximum possible boost depends on the fuel's octane rating and the inherent tendency of any particular engine toward detonation. Premium gasoline or racing gasoline can be used to prevent detonation within reasonable limits. Ethanol, methanol, liquefied petroleum gas (LPG), and compressed natural gas (CNG) allow higher boost than gasoline because of their higher resistance to autoignition, lower tendency to knock. Diesel engines can also tolerate much higher levels of boost pressure than Otto cycle engines, because only air is being compressed during the compression phase, and fuel is injected later, removing the knocking issue entirely. Motorcycles. Unique design considerations for motorcycles include tractable power delivery, and packaging for heat removal, space conservation, and desired center of gravity. See also: Jet engine.